we're going to go over a review of fractions. Okay. So, there are two ways that we can reduce this. One is we can find something called the greatest common factor. Okay, so greatest common factor. And basically what that would be is the largest number that we can divide both into 20 and that we can divide into 25. So for instance, I can divide 20 by 1. I can divide 20 by 2, by 4, by 5, by 10. See? And you can actually check this on your calculator, right? So again, I'm just saying I can divide it by 1 evenly. I can divide it by 2 evenly. Right? I can divide it by 4 evenly. I can divide it by 5 evenly. I can divide it by 10 evenly. And of course I can even divide it by itself. Okay. Now as far as 25 goes, we can divide 25 by 1. Doesn't do any good, but we can do it. We can divide 25 by 5, which gives me a 5, and we can divide 25 by 25, which gives me a 1. So the greatest part, the GCF, the greatest common factor, would be, these are factors, right? Factors we can divide into it, or numbers we can multiply together to get the original number. So we have quite a few factors here, and what we're seeing is that this factor here, which is 5, and this factor here, which is 5, is the largest common factor of 20 and 25. So what we would do at this point is we would simply divide both of these numbers by 5. And what that would give you is, that would give you 20 divided by 5 is 4, and 25 divided by 5 would give you a 5. And then this is now in terms of lowest terms. Okay, so let's try the same way on the second one. So the next one is I can reduce 5/15 by, I can divide the numerator by 5 and the denominator by 5, and that would give me 1/3. And we have, okay, so that's one way to do it. The other way of doing it is something called the prime factorization. So prime factorization. Okay, so basically what that means is there are prime numbers like 1, 2, 3, 5, 7, 11, 13, 17. There are an infinite number of prime numbers. Prime numbers are simply numbers that you can divide by both themselves and 1. So I can divide, well, 1 is technically prime. That's a little more complicated, but 2 we can divide 2 by 2 and 1. 3 we can divide 3 by 3 and 1. 5 we can divide by 5 by 5 and 1. 7 we can divide 7 by 7 and 1. And nothing else, right? The reason you don't see, for instance, 4 here is I can divide 4 by 2. The reason you don't see a 6 right here is because I can divide 6 by 2 and 3, right? So anyways, so one way that we can do is we can take the number, and this is a much more advanced method. We're going to use this more later on, but I'm just going to introduce it now. You don't have to use it right now. You can use it later on when it's required. So what you do is you take the first prime number, like 2, and you try to divide it in there. You can do the same thing with branching. There's different methods. I like this because it's compact. So we say 20 divided by 2 is 10. And then we try 2 again. Can I divide 2 into 10? Yes, I get a 5. Can I divide 2 evenly into 5? No. How about 3? No. How about 5? Yes. And we get that. So the prime factorization of 20 is 2 times 2 times 5. Okay, now we do the same thing with the 25. So can we divide it by 2? No. Can we divide it by 3? No. Can we divide it by 5? Yes. So we divide 25 by 5, and we get 5. Then we divide 5 by 5, and we get a 1. So you know we're done, we get a 1 at the bottom. So we get a 1 there, and we get a 1 there. Okay. So what we do is we go back and we rewrite the original one, and you don't have to do it both ways. I'm just showing you two ways of getting a solution. Either way will work. You do not have to do both ways. So the point I'm trying to make is, let's say we had 20 on top, and we say instead 20 is equal to 2 times 2 times 5. And on the bottom, we still have the 25, but we break that apart and do 5 times 5. And we cancel out the 5s. The same thing on the top and the bottom, the common factors in the top and the bottom. and whatever's left over is the answer. So now we say 2 times 2 is 4, and we say 5, and there's nothing else there. It leaves us a 5, and we're end up with 4/5. All right, so that's another way of doing it through prime factorization. Okay. So whenever the fractions are pretty small, probably just want to use a common factor, the greatest common factor. As they get more complex, you may have to move on to using the prime factorization method. Okay. So this one right here is saying write the improper fraction as a mixed number. Okay, so what we're going to do is we are going to take the numerator and we are going to divide it by the denominator. So I would say 17 can go in there, looks like 6 times. Okay, and 6 times 12 is a 72. We subtract 72 from 77, we get a 5. I cannot divide 5 by 12, so that is a remainder of 5. I'm not trying to get a decimal. Now what that does is that means that I have a whole number 6 and the 5 remainder I put up on top. And all you do is you put that 5, that remainder, above the 12, which was the original denominator. You simply stick it right back over the original denominator. So you end up with a mixed number of 6 and 5/12. Okay, so we want to write the improper fraction as a mixed number in simplest form. So the next one, number 4. So what we do here is, again, we divide. So I'm going to say 17 divided by 7. So 7 goes into 17 twice, right? 17 minus 7 is 10, minus 7 is 3. So you could do repeated subtraction if you're struggling a little bit with division. So I know it goes in there twice because I can subtract 7 from 17 twice. And 7 times 2, or 2 times 7 is a 14. So 17 minus 14 is a 3. I cannot divide 7 into 3, so I know I'm done. That's my remainder of 3. So we keep the 2 as the whole number. 3 is the new numerator, and we stick it back over the old denominator, which is a 7. And we got it. Now we want to write the following mixed number as an improper fraction. Okay, so we're going to do the same thing we did with turning an improper fraction into a mixed number, but in reverse. So we're going to take the whole number, we're going to multiply it by the denominator, and then we're going to add the numerator, right? So again, we're going to take the whole number, multiply it by the denominator, and then add the numerator. So 8 times 2 is 16. 16 plus 1 is 17. And we stick it right back over the old denominator of 2. Okay, so again, I'll rewrite 8 times 2 plus 1. And you can see where we got all the pieces, right? Got all the pieces. Okay. So let's try the next one. So we're going to find the product and write it in lowest terms. So what we do when we're multiplying fractions, we multiply straight across. We say 2 times 1 is 2, and we say 9 times 7 is 63. Now, since we can't divide something into a 2 and a 63 except 1, in other words, the greatest common factor of a 2 and a 63 is a 1, we know we're done. So that's when you know you've simplified it or you have it in the lowest terms. Okay, so let's try to multiply the next one. Now, oftentimes before you multiply, it's a good idea to see if you have a common factor in the numerator and the denominator. For instance, I have 105 in top and I have 42 in the bottom. So the question would be, do I have any common factors in the top and the bottom? So I can divide both of those by 7. So for instance, 105 divided by 7 would give me, let me read over here. So 105 divided by 7 gives me 15. And I can also divide 42, right? 42 divided by 7 gives me 6. Ah, looks like I probably could have gone a little higher, right? So this isn't bad that this happened. All this really indicates is I didn't get the greatest common factor right off the bat, which means I can kind of chip away at it. So I'm trying to reduce this fraction right here, right? So since I can divide both 15 and 6 by 3, it turns out it wasn't quite done. What it really looks like is I probably could have So in one step, it would have been, I can divide both these by 21, right? And that would have given me a 5 and a 2. But let's say I didn't know that. Let's say I made that mistake, right? And instead, I divided this one by 7. I divide both these by 7. And what I would have gotten instead is I would have gotten a 15, and I would have gotten a 6. Well, that's fine. You're just not done, right? Because yeah, I can simplify 15 over 6 again. So I would divide both these by 3. And what that would have given me is a 5 halves. So you can use the greatest common factor on simplifying these fractions. And if you didn't get the greatest common factor, but you got a common factor, you can actually simplify them repeatedly using the same method, right? So you can, if you can find anything but a 1 that you can divide into the numerator and the denominator, you can use that to start the process of simplification, and you just kind of break it up into multiple steps instead of doing it all in one step. Okay, so it looks like this first one, the first 105 over 42, you can reduce that to 5 halves. Okay, now what can we do with the 14 tenths? Well, it looks like I can divide both of those by 2. Sorry about my handwriting. So what we get is a 7 over a 5. Okay, so what we end up with is a 7 over a 5. Now these are being multiplied together. Now what we can do after that is we can see if anything will cancel out with these as well. Well, it looks like we have a 5 on top here, and we have a 5 on the bottom here. This is quite similar to whenever I was reducing one of the original fractions by prime factorizations. So in prime factorization, if I have, right, prime factorization is what I did right here. If you have a common factor in the top and the bottom, you can simply cancel them out. So all I'm really doing is, since when I multiply the numerator through, that's all going to be on the top, and when I multiply the denominator by, that's all going to be on the bottom. All I did is I just canceled them out, right? Because again, that 5 on the top and this 5 on the bottom will be there, so I'm just canceling that before I multiply instead. And then I just end up with 7 over 2. And then that's simplified.